Okay, this part of the course we are looking at discrete random variables and discrete distributions, probability distributions. So there's two in particular I'm looking at, the geometric and the negative binomial. In fact, in this video it's the negative binomial. So the main two are the ones that you will probably be meeting first off, with the Bernoulli distribution and the binomial distribution, and they are both related to counting the number of successes in one or more trials. Now, similarly, the geometric and the negative binomial distribution are also related are related in a number of trials needed to get one or more successes. Okay, so they're sort of asking the same sort of questions, or tackling the same problem from a different approach. So the negative binomial distribution refers to the probability of the number of times needed to do something until a fixed number of results is achieved. For example, how many times will I throw a coin until it lands on heads for the 10th time? How many children will I have when I get my third daughter? Or how many cards will I have to draw from a pack of cards until I get the second joker? Okay, so there's two controlling parameters, just like in the binomial distribution. Let's scroll down here for a second. They are the probability of a success, P, in any independent test, and also the desired number of successes. Here I'm calling it M. Okay, and I'm being deliberately awkward actually, because in other videos I'm going to call it R and S. And the reason for that is, unfortunately, statistical notation is not consistent, and I just might as well sort of give that reality to you. Okay, if you're looking at books, it might come up as R or S. Okay, P is usually probability though. Luckily that stays fairly constant. Anyway, so we'll go with M for this video. If a random variable X has a negative binomial distribution with parameter P, probability, and M, number of successes, the probability mass function is as follows. The probability of X equal to N, okay, is N minus 1 divided by, or it's N minus 1, choose M minus 1, okay, times P to the M times 1 minus P times N to the minus M. Okay, now sorry, M is the number of successes. Okay, N is how many trials, so N is number of trials. Okay, number of trials. And that's what we're asking for ourselves here. Okay, so the number of trials required to achieve M successes. Okay. Now, so it's very similar to the binomial distribution. Anyway, quick working example just to sort of get us going. A traveling salesman goes home if he has sold 3 encyclopedias that day. So that's his daily target. Some days he sells them quickly, other days he's out late in the evening. If on average he sells an encyclopedia at 1 out of every 10 houses, so P equals 1 divided by 10, 0.1, he approaches. What is the probability of returning home after only visiting 10 houses? Okay, so here the number of trials, X, is a negative binomial random variable distributed with parameters P equals 0.1 and M equal to 3. So he's trying to figure out how many trials, or how many houses he needs to visit before he can sell 3 encyclopedias. This looks like a tall order, but let's find out. So we were interested in what the probability that the number of trials required, the number of houses that he has to visit to sell 3 encyclopedias is 10. So probability of X equal to 10. So that is N minus 1, choose M minus 1. So 9, choose 2. That's 10 minus 1, choose 3 minus 1. Okay. And times 0.1 to the power of 3 times 0.9 to the power of 7. And that actually works out to be 0.0179%. So essentially, very rarely is he going to sell that many encyclopedias that quickly. Okay, So that's just checking that formula again. So that should be 45, 9 choose 2. No, it's not. It's 72. Better not do this stuff in my head. Anyway, so it is 36 actually. So 72 times 0.1 to the power of 3 times 0.9 to the power of 7. I shouldn't be attempting that without a calculator, but there you go. I have the answer written there. It is 1.7%. Okay, so that's just using this formula up here. Okay, so that's a quick introduction to the negative binomial distribution.